I was going to say that you were working in liquid art. That's exactly what I was going to say. And so he started in liquid art. And then he saw the light and he worked with us first as a Letterman Fellow and then as a Wilson Fellow at Fermilab. Somehow managed to get the two fellowships, one of them another. He worked in Pico. And the way I like to describe Hugh is that he's the person who made the difference between our largest bubble chamber so far, Pico 60, going from not really working to producing world-class sort of results. I give him credit for that. After that, he went back to Noble Liquids, and he's been working as science coordinator, is that correct?
Physics coordinator.
Physics coordinator for LC.
No longer. I'm done with that.
Could you introduce yourself?
Okay, I'm almost done. I'm almost done with this. I even told you before.
At least we spared the money.
You know, I'm the host for most speakers this quarter, so get ready. So he's now been working on LC as a science coordinator. And we catch him. This is a revolt now. We catch him 4 days before leaving for Santa Barbara. He's becoming faculty at UC Santa Barbara, and for me, this is a way to say farewell. So many years of having him around the corner, and I'll be able to self-invite myself to meet for Santa Barbara. So this moment for that. Anyway, today he's going to tell us about something that may not be the party line.
Yeah, the talk's schizophrenic. Can you guys hear me? Is it too loud or is it good? Okay.
And I'm done.
Yeah, okay, so Juan asked me to give this talk 2 weeks ago, and I was moving, and I was like, there's no way I could do it. But then I remembered he had a germanium counter, and so last weekend I brought over some illegal bottles of tritium and xenon, activated xenon for him to count his counter. So that's the quid pro quo in this arrangement.
My office is a slightly big
Okay, so obviously this will be somewhat informal. Feel free to interrupt whenever you want. There are way too many slides. As I say, it's schizophrenic, so I'm going to do a little bit of background on dark matter. I'll talk a little bit about LZ. I'll talk about some doping of LZ, and I'll actually talk about actual doping of xenon, which is very new, and I don't know what's going on. Okay, is this working? Goes backwards. Okay, we believe dark matter exists. So the most discussed candidate still, I think, is probably the nuclear interaction massive particle. Most people in the room are probably familiar with this, but just to quickly summarize, the idea is that early on in the universe after the Big Bang, everything was in equilibrium. As the universe expanded and cooled, the dark matter basically fell out of equilibrium and started annihilating away as the universe became too cool to produce it. Then at a certain point, they can no longer find each other to annihilate, so the amount of dark matter, the number, has been constant since that time. And so they're still around today with sort of canonical densities of about a few per liter. So if you make a fist, by density, there's a dark matter particle in your fist. There's actually a lot more because they're moving faster than that, but anyway. Okay, so how do we find it? And generally, I'm going to talk today about direct detection, which is the idea that these particles that are in my fist can actually bang into something and maybe I can detect that. So we calculate, the way this one works, I'm going to go fast, forgive me, but we're going to go through it as best we can. So you calculate the rate based on assumptions we make about the dark matter distribution interaction. So we sort of say we know how much there is. If we sort of make a hypothesis about the interaction, we can calculate a rate in our detector. There are historically two interactions that we sort of consider. This is known as spin independence, which means it couples to all nucleons. And enhancement means that for large nuclei, because it's coupling to all the nucleons, you get enhancement. I'll come back to that. And the other thing we think about is spin dependent, which couples to the spin of the nucleus. So that's an unpaired spin and of one nucleon, so you do not get this enhancement over all nucleons in the sort of same way. Maybe I'll come back to that. All right, so this rate, and this is, I think, one of the only slides with equations on it, but I think it's important to know how we think about these things, particularly for the first year graduate students. So the differential cross-section, this is for spin-independent interactions in events per kilogram per KeV per mass, DRDQ. So this is just the rate of events in your detector per unit energy. It has 4 terms in it. The first term is rho over m. So this is the dark matter density. Rho is the density of dark matter in our universe, in our galaxy, m is the mass of the dark matter candidate. So this is literally just the number of dark matter particles going through your detector. So it's a straight up scaling. We measure this from galactic observations, and there's historically around a factor of 2 uncertain in this number, but again, it just scales the sort of overall rate up or down linearly. The second term is the particle physics component. In an ideal scenario, what we would be doing is measuring a rate, inverting this equation, and then being able to say something about, might just be about, I'm just going to yell. We'd say something about this particle physics. So sigma naught is the cross-section. That is the likelihood with which dark matter is going to interact with normal matter. That's the particle physics we're trying to measure. And I've written in here explicitly this a squared component. So that's the atomic number of the nucleus, atomic mass of the nucleus. So that's that coherence I mentioned. That for big nuclei, you get a coherence across the whole thing. You get an enhancement of the rate. And so that's the particle physics. Now, for me being a particle physics, I do not understand a thing about nuclear physics, but that doesn't mean that physics doesn't care about nuclear physics. And so there is a component we have to include for that. So this is the nuclear form factor, which is expressed here by this S squared of Q. And this is accounting for the fact that as the de Broglie wavelength of the momentum transfer between the interaction gets small, it can get small compared to the size of the nucleus, and you lose that coherence. So instead of interacting with all the nucleons, you now lose the coherence, and this is accounting for that. And just to give you a sense of scale, it goes roughly sort of exponential, where the bottom of the exponent looks something like this. So it happens faster for large nuclei, and I'll show you that in the plot in a second. And then the last term is the velocity distribution. So this is effectively sort of somehow encompassing the fact that a dark matter has to be going fast enough to bang into your target and deposit enough energy to be visible in your detector. And dark matter has some velocity distribution in our galaxy, and so you have to integrate over that to determine the rate of events that you see in your experiment. Okay, so we're on energy scales. So the energy of the recoils we're looking for is order keV. That's entirely driven by kinematics. So kinematics will be something I come back to a lot in this talk. We're looking at the simplest process you can imagine. It's elastic scattering of two things. And so if you have elastic scattering of things with, say, approximately similar masses, and the speed with which we think dark matter moves in our galaxy, you come out with something like 50 keV of energy deposition. That's the scale of the recoils we look for, which is very low by sort of classical particle physics standards. Okay, so here's a plot. This is the integrated rates above some threshold for a 100 kilogram target at this cross section. So these units, 10 to the minus 46 square centimeters, this is about a little bit above the current best sensitivity. So we're actually probing deeper than this in cross section. This is a very, very low cross section. And this is sort of what you would see about a 100 kilogram size detector if the dark matter was 100 GeV. And I've done it for 5 possible target nuclei, so xenon, germanium, argon, silicon. So the first thing you should notice is that there's not very many counts, right? These are real numbers. There's something like a couple of counts per year in this detector at this cross section. So it's not very common. The second thing you'll notice is that xenon, which is the highest A target on this list, has the highest rate. That's because of the coherence, that you get this enhancement to A squared. But you'll also notice that it falls off faster as you go up in energy. And that's the nuclear component coming in, this form factor. So because xenon is the biggest nucleus, it loses its coherence at lower energies than the other targets, and so it falls off. Now this rate depends crucially on the wind mass and the threshold. So if instead of having 100 GeV target wind mass, I had a 10 GeV wind mass, this is what the plot looks like. So all these rates now fall off very fast with energy. And the reason for that is essentially kinematics again. It's hard for a light particle to give a significant amount of energy to a heavy nucleus like xenon because of kinematics. It's like a ping pong ball bouncing off a bowling ball, and so you don't get very much energy deposition. That's why that falls off so fast. It means that knowing your energy scale efficiency and threshold is crucial to doing these experiments. Something that Juan took great pains to point out many, many years ago to many, many people in as loud a way as possible. Okay, so this is the plot you always see in every dark matter talk. Every dark matter talk, direct detection, you will see this plot. And so let's talk about it a little bit. On the y-axis is the cross-section again. That's that particle physics component. This is the expression of how likely it is for dark matter to interact with a nucleus. On the x-axis is wind mass. Again, we don't know what we're looking for, so you can scan over many wind masses. And what you generally will see is these lines that sort of look like lounge chairs. And they always have the same characteristic shape. And the reason for that is that at low mass, so at the low end, they shoot upwards very, very quickly. And that's because you're limited by threshold. So every detector has some minimum energy that they can see. Below that energy, you can't see anything. And it's very, very hard for a 1 GeV dark matter particle to give a significant kick to a nucleus of the detector, and so you can't physically see something that small. At high mass, they go off linearly in principle forever, and that's because you're limited by density. Remember, the density is something we get from the Milky Way. We measure that, so that's fixed. So the heavier the dark matter particle, the fewer of them there are to interacting with your detector, and so you lose sensitivity just because there are fewer of them interacting. Then at the bottom, this so-called neutrino coherent scattering line, that is a background that we will run into, which is effectively the exact same process where a neutrino coherently scatters off the dark matter, and it will look very, very similar to dark matter in our detectors, and so that's sort of a lower line on, roughly where we think we can get to. Okay, so that is the first section of the background. Any questions? Yes?
Is there an update since 2000?
No, nothing's happened since 2000. Okay. So we look for WIMPs. Many WIMPs have been going through us as we've been having this lovely conversation, but we might expect only a few counts of the detector per year. So what's the issue? The issue is backgrounds. So background radioactivity is everywhere. When you become a dark matter or low background neutrino physicist, you'll learn about this. It really sucks. So bananas have potassium in them. If you own your own home and have radon in your basement, radon really, really sucks. If you have a Geiger counter on the surface, it goes off something like 100 times per second per kilogram. That is something like 3 trillion events per year at a ton scale detector, and you're looking for 2 events. So that's the problem. That's why this is hard. And it's not that easy, unfortunately, to find a needle. So what are the background sources? Some common ones that we know about. So cosmic rays constantly streaming through us all the time. So nowadays, all these experiments go underground to get away from them. So these are pictures from Snow Lab, where I used to work when I worked with Juan, where they built this crazy 1980 science fiction movie in 1,600 feet below the Earth. So that's pretty cool. But you work with a bunch of miners. All these experiments are underground. Okay, what next? Radioactive contamination. I mentioned radon, rock, impurities. So there's an emphasis on purification, making sure that you get nothing that you didn't intend to get into your detector, because that will likely be radioactive. So here's a couple of pictures of, this is the CDMS experiment, this is the Lux experiment. You can see the clean room garb that these guys are in to make sure that nothing that they didn't intend to introduce in the detector gets in, because that will give you backgrounds. And then lastly, you do have to actually build your experiment out of something. You can't get rid of everything because you have to take data. And so steel, glass, for example, photomultiplier tubes, other components, these are also radioactive. And so what can you do about those? The 2 big things is self-shielding. So in this case, you have a large sort of target volume that's monolithic, that you're detecting the signals at the edge, and you can shield itself. So things at the center are shielded by the xenon at the edge. I'll come back to that. The other thing you can do is discrimination. Is there something you can use to tell the signal from the background? And this is a big key to sort of modern dark matter experiments. So this plot I've stolen from CDMS shows what I'm talking about. So this is a nucleus with electrons orbiting around it. And in dark matter, we're looking for the dark matter to interact with the nucleus. So we call that a nuclear recoil, or an NR, and I'll use that window throughout the talk, where it's the nucleus that's carrying in your detector. Most of your backgrounds comes from gamma rays or betas, so photons or electrons, and those interact with electrons. And so it's the electron that recoils through your detector. Let's call it ER, again, I'll use that window throughout the talk. But if you can tell these 2 things apart, then you can pick out your signal and reject your backgrounds. So these are 3 ways that it's been done in the past. They're not the only ways. So this is an example. CDMS, I've mentioned before, these are cryogenic bolometers, so they're super cold. They measure charge and heat, and the ratio of those 2 helps them define what the interaction was. In the xenon TPCs, which I'll talk more about, we measure charge and light, and the ratio of those 2 things you can play against to do discrimination. In liquid argon, you can use the timing of the light that comes out to do the pulse shape discrimination, to tell apart, again, nuclear recoils from electron recoils. So most of the big experiments have to do this kind of discrimination these days to make progress. Okay, so if you wanted to design a custom dark matter detector, what would you do? So here's the challenge, and here's a solution. So the first challenge, of course, is extremely rare. So you're looking for something that never happens, so you need a very large target and scalable so you can get as much mass as possible to search for the thing. You're looking for low energy deposition, so that means you need low energy thresholds in your experiment. Then you have several sources of backgrounds, so you want to be able to purify, shield, and discriminate against backgrounds to get rid of those. And then lastly, you don't actually know what you're looking for, so it would be nice if you had sensitivity to multiple types of interaction in your experiment. So now I'm going to talk a little bit about Xenon TPCs, which I think check all the boxes on that list. Any questions before I start that? Everybody's happy? All right. So a two-phase Xenon TPC. So TPC, I'm using jargon, I apologize. A TPC is a time projection chamber. And I will define that in 2 seconds. But basically what it is it's a right cylinder of xenon, where you have a liquid component and then there's a gas component, hence two-phase. And what you do is you put an electric field on the liquid, and you have a second electric field in the gas. And so an interaction in the xenon, a particle comes through, bangs into something in the xenon, creates a flash of light, which we call scintillation light, or S1. So that happens almost instantaneously. You also create ionized electrons. And because you put an electric field on the liquid, you drift the electrons to the surface of the liquid, you pull them into the gas, where they get accelerated by the second field and make another flash of light. This is called S2. And so you get a single S1, followed by sometime later by this big S2 pulse. Now the drift time here indicates the depth, so that's why it's called a time projection chamber, because you can take this time to figure out where it happened in the detector. Okay. So why are these things nice? Well, first you get excellent 3D reconstruction. So the hit pattern in the top here tells you where in XY it was. And I've already mentioned you get Z from the drift time. So that allows you for self-shielding, and I'll come back to that in a second. And the second thing is that the ratio of charge, as represented by S2, to light, as represented by S1, gives you particle ID. And so you can do really good rejection of ER events using this technique. So a few comments on this. First, self-shielding in xenon is really, really powerful. Xenon is very dense. It's about 3 kilograms per liter as a liquid. There's a lot of electrons for things to hit. And so if you have something like an MEV gamma ray, and you want it to come in and deposit something like a keV of energy, it doesn't get scattered very much, so it has to go fully across the volume, again, without interacting. So this is a hit map from the Lux detector, which was about 300 kilograms of xenon. You can see all of the events pile up at the edge, and there's very few single scatters in the middle because it's very hard to get all the way through the detector without hitting anything again. So the self-shielding in xenon is just really, really powerful and nice and clean. Here's the discrimination. I actually sort of hate the way we do this plot, but this is the way we do it, so I apologize. So these are 2 different calibrations. So the top panel is an electron calibration. The bottom panel is a nuclear recoil calibration. The scales are the same, and the lines appear in the same place, but the data, of course, is from a different calibration. So let's just give the bottom line, which is here at the top, where you're calibrating electronic recoils, their mean is along this blue band, whereas the dark matter is going to populate this red band. And so what you're looking for is ERs leaking below this red band, and that's your discrimination there. So you can separate them very clearly using this technique. Okay, so let's just do a sort of punch card. So extremely rare means you want a large mass. Liquid's really nice. It's very dense. You can get 3 tons in a meter cubed. So basically, if I put my arms like this and I wrap it around xenon, that would be a ton of 3 tons of xenon. So that's really, really dense. You can do a lot in a small place. All right, low energy thresholds. That S1 and S2 process I talked about is actually quite copious. You get something like 70 electrons and photons per keV. That's quite a lot to be collecting. Purification. Noble gases don't interact with anything to do by definition, so they're pretty easy to purify. Self-shielding, I've talked about, is fantastic. There's a low mean free path for ionization, ionizing radiation. Discrimination is pretty good. And then lastly, the sensitivity to multiple types of interaction. So the high A is great for spin independence. There are also many isotopes of xenon, so you can actually see other things as well. So xenon's a really nice target for this kind of stuff. All right, any questions on that? Yes?
Why you need TMT both on the
Mainly to collect as much light as possible for the threshold, which I'll come back to. But you want to basically see as much S1 as you can in the detector to maximize the signal. All right. So a few words on LZ, which is the experiment I work on, which is directly competitive with Luca's experiment, xenon and sun. They really hate each other. So LZ is going to have 7 tons of active liquid xenon. All these detectors look basically the same, just to keep that in mind. So in our case, we have a bottom PMT array, a top PMT array, several grids. There's some reflector around it. Then that thing sits in a cryostat because liquid xenon is at 165 Kelvin. Then that thing sits inside, in our case, it's an outer detector of liquid simulator. That's to catch neutrons for background rejection. That all sits in a water tank, again for shielding. Then that water tank sits a mile below the Earth for getting away from cosmic rays. So there's a huge effort to make this thing clean and low background, same for Xenon as well. So here's just a close-up of that. I won't dwell on the particulars. So here's the 10-slide flash forward through the progress of LZ. That's basically all I'm going to talk about it, but here's some pretty pictures. So where are we? The TPC is built. So that is a great thing, and we're all very happy about it. So this started last December. Many thousands of hours in this class 1000 clean room in a reduced radon environments, bringing many tens of thousands of tiny low background components together into a single object. So here are the PMT arrays. There's about 500 3-inch photomultiplier tubes. This is the skin detector. So this is something actually I was responsible for going back to this. So the TPC is at voltage in something like 50 kilovolts. So we have to, then it's just in a cryostat, which is at ground. So you have to hold off that voltage, which means there has to be some dead layer of xenon. But we don't want that to be dead because, as I've already mentioned, xenon is a really good absorber of radiation. So we actually instrument it in what we call the skin. And so we tiled the cryostat with Teflon. Teflon is a really good reflector, which I didn't mention. But we use Teflon everywhere. And then we put PMTs to look at the skin. The grids were woven using a specially built loom at Slack. So that was possibly the most complicated part of the experiment, I would say. There are 4 meshes using 75 or 100 micron wire. There's a major QA program to make sure that this was clean, was up to spec, and this was, drove the critical path for a while. Everybody was pissed off each other, but it was successful. They were delivered, and now they're installed. So that's, I think, a big success. Here's some pictures of actually doing the installation. So this is the field cage being built. Here's the grids being put on. The extraction region where we pull the electrons into the gas and multiply them. Here you can see some of the grids, this is mating the extraction region onto the main body of the TPC. Everybody's holding their breath. And then finally, it's all put together with a couple of these details. So that's done. And then here's one quick picture of what it looks like underground right now. So this is another thing that I was responsible for. It's basically a glorified heat exchanger. This is a test cryostat that I was telling you a little bit about earlier. So we're going to be doing some testing of the cryogenics coming up in the next few weeks as well. So the schedule, the detector is assembled on the surface after many, many years of design and construction. The insertion in the inner cryostat occurred a couple weeks ago. I think we plan to start taking physics data in mid-2020 and keep an eye on it. All right. One slide on Xenon N-ton, which I stole from TAP just to make sure we all know where we are. Xenon N-ton is the successor experiment to Xenon 1-ton, which was a very successful Xenon TPC that currently holds the best results in the field. And lo and behold, they are also on the same schedule. So we're all racing to get the next chunk of parameter space, and it'll be interesting to see what happens. And I would be remiss if I didn't mention yet a third experiment that is identical in almost all respects being built in China. The Panda X experiment, Panda X 4-ton, and they're also under construction, maybe a little bit behind, but anyway, we're building 3 of these for better and for worse. All right.
Who has more miles of cable?
We have something like 12 meters, 24 meters of cable per PMT over 500 channels. So, it's like, several. The cables are a giant pain in the ass. But I think if we do this again, we have to do something about the cable. We can't survive like this. Question?
Derek?
So, maybe this is silly, but like, if they're all so similar, I feel like there has to be like some differences that are like why they don't
That's a very good question. The answer is political. I think mostly, there's a couple answers. The optimistic scientific answer is, well, when we discover something, we'll want to make sure we can confirm it. And wouldn't it be great if we had 2 experiments or 3 experiments that can confirm that we've all seen the same thing, and therefore, everybody's happy.
It would be better if we discover you.
Right. The other part of the answer is that a lot of the people who were in these experiments couldn't get along. And at one point they were together, and then they split up, and now there's a lot of bitterness, and that still persists. So it's not great. But I think there is some scientific value in having 2 if we see something. In the meantime, actually, it was really helpful to have Xenon N-ton because it convinced the DOE to give us money faster. So we didn't have to spend an extra 3 years building it because we're like, look, these guys are building it, give us the money, and they did. So, okay, so here are some projections. Everybody loves projections in these talks, and I'll have some more later, don't worry. All right, so this is LZ in orange and Xenon, best case, in purple. And you can see they're basically on top of each other. Okay, and then dark side 20K is a liquid argon detector that's also under construction, or starting to be under construction a few years behind. I'm not going to talk about liquid argon unless it has to be yet. This is what the next generation will do. And I should have had the previous lines on here, but again, we're currently sort of around the, just below the 10 to minus 46 square centimeter. All right. So where are we? This is like the Moore's Law plot of dark matter over the last 30 years, I guess 40 years now. So we initially had some detectors, classic low background detectors with no discrimination. Then we got discrimination in the slope change. And in the last 10 years, it's been mostly dominated by liquid xenon detectors, which have been the best in the field in the spin independent region, pushing things down. And we hope to get down to something like 10 to minus 48 square centimeters in the early part of the next decade. Okay, so this is maybe, well, I like to skip through this part because some people will be knowing I've been around out of time. But I'll give a quick, all right, I'll just go through this next 3 slides and then I'll skip a bunch of stuff. Okay. So we talked about weakly interacting massive particles at the beginning. Of course, the thing is that we actually understand what the weak interaction is. It's a known process. Say if you were exchanging a Z, you can write that down and say, well, how big is that coupling? And it's on the order of 10 to the minus 39 square centimeters. That's up here in this plot that hasn't been updated in 10 years. So that's been ruled out, right? So classic simple Z exchange is more or less ruled out. We're not looking for the weak interaction anymore. However, what we could be looking for would be something like that couples proportion to mass, like the Higgs. There you can get a suppression down to sort of 10 to the minus 45 square centimeters. Don't take these blobs literally, of course. This is just blobs on a plot that's got orders of magnitude on the axes. But that's down here. And so I think what we're doing right now is saying, will the dark matter couple at order 10% to 1% to the Higgs boson? That's what we're sort of looking for now. However, if you open up your axes a little bit and say, well, what could the dark matter be? Here is a plot. Well, what do we know actually? What do we actually know about the dark matter? We know it interacts via gravity. We know it's dark in the sense that it's not interacting strongly with light electromagnetism. We know it's really collisionless. We know it moves pretty slowly. It's not real viscous. So here's 50 orders of magnitude on either axis of possible dark matter candidates. This is what we're looking for. It's probably WIMPs, right? That's the conclusion, which is not actually true, but we don't actually know what we're looking for. So this is another updated SOMS plot. Over here you can see the current best lines. Actually, this is out of date. This is the goal of LZ. So what's happening is that we've really made a lot of progress, right? Here's the neutrino floor. We've gone down many orders of magnitude in the last 20 years, and the way I'm sort of thinking about it is the classic Monty Python, not dating myself, Monty Python sketch where, at the end of every sketch, a foot comes down and stamps everybody to pieces. And so what happens is we're squirting out because we're getting smashed against the floor. And here's my only illumination of the whole thing. And so all of a sudden, we're getting squeezed into this low mass range, which is much less constrained. Okay? So now I have a whole sequence of slides which I stole from Gordon Krumyak on light dark matter. I'm going to skip them because I'm not going to run out of time. Let's come to the conclusion. So the conclusion is light dark matter is interesting to look for. Okay, thank you. Thank you, Gordon. Any questions on that? Okay. So if you take my word for it, or those previous slides that you didn't get to see, that light dark matter is an interesting topic. The next question is, well, what do you need to look for it experimentally? As an experimentalist, that's my question. So if you remember this plot, this was the energy threshold, the rate versus energy for 100 GeV dark matter. And then when I went to this plot at 10 GeV, everything fell off much, much faster. So the answer is that for light dark matter, you need very low thresholds. And the reason for that comes from this, the fourth term of the equation I had earlier from the velocity term, is that effectively, again, it's hard for a low mass dark matter particle to give enough of a kick to a heavy nucleus to be visible in your detector. So you want, you need very low energy thresholds to be able to see them to the small kicks that can be given by this target. And so this term is just an integral over the velocity of dark matter in our galaxy. And it's got a low cutoff, which is your energy threshold Q, which is sort of roughly proportional to the mass of the nucleus, so the square root of the mass of the nucleus. And it's got a high cutoff from what we think is the fastest dark matter that can be bound in our galaxy. And so what this is pushing you towards is first, as I say, low thresholds, but also you want a low mass target so it can have a better kinematic match to the dark matter mass. Because of that, for a given threshold, the velocity is minimized when the masses are the same. So I'll just show you this graphically. Is that what you want is low thresholds and you want light targets. So here is, in some different context, the maximum recoil energy that can be deposited in your detector. So basically your threshold has to be lower than this value to be able to see this thing as a function of wet mass. For xenon and orange, and then helium and hydrogen in these other lines. So what you can see is that if you're looking for something like a 1 GeV dark matter particle, the energy threshold in xenon has to be sub 100 eV, whereas if you're looking for a lighter target, you can be up in a kV regime. So that's the kinematic scale. I think I just wrote it in words here. So for the same WIMP mass, hydrogen, the maximum recoil energy is 100 times bigger than it is for xenon. So you can see much higher, you're able to see higher energy recoils and so have sensitivity. Sort of by the same token, for the same fixed recoil energy, you're sensitive to 11 times lighter dark matter targets. Again, this is all coming through kinematics. As a sort of side note, you're also less sensitive to uncertainties in the halo. So I've been talking about our model for how dark matter is moving through our galaxy. Turns out we don't actually know that all that well. We know it somewhat, but there are, particularly in the tails, there can be variations. Things are coming out of the Gaia experiment right now. They're telling us more about that. And just for example, so this is our sort of standard halo model of what dark matter looks like in our galaxy. Remember we were doing an integral from a minimum velocity. So for A equals 129, so that's xenon, this is what V min is. So this is the part of this curve you're integrating to get your rate, which obviously is very sensitive to uncertainties in the tail. If you have a light dark matter candidate, or sorry, light target, so A of 4 for helium would be slightly lower for hydrogen. This is the part you're integrating. And now you don't care so much about the tails because you're getting much more distribution. So you're much less sensitive to these uncertainties than the light target. Okay, so back to the custom dark matter detectors punch card. What if there were custom light dark matter detectors? So what do you need? Extremely rare interaction. We said we're going to large target mass and scalable, but I've crossed out large. Why is that? The answer for that is because for regular dark matter, for sort of 100 GeV classical dark matter, we're down here, you need 10 tons of xenon to get to that. But up here, there are no limits. And so you don't actually need very much mass. A kilogram of hydrogen, for example, is up here, where again, there's no limits here. So you don't need a large target mass for light dark matter, at least not yet. Okay, you need energy depositions of a keV or below, so that's very low energy thresholds. You need all the same background rejection you had before, and then I added this kinematics because you want a light target to maximize your sensitivity. Okay, so back to LZ. Nice things about LZ, it's big, it's clean, it's actually going to exist, which you should never take for granted about anything. But the problem is it's a heavy target, so that was a nice, it's a big heavy target, which is good for 100 GeV dark matter, but not so good for 1 GeV. Wouldn't it be great if you could add a light atomic target to LZ or xenon atomic or anything else? So this is the idea, hydrogen doped xenon, or we call it hydrox. Okay, so dissolving hydrogen in liquid xenon. Before I go ahead, any questions? You all with me? Yeah? Yes?
Why just build a,
Why not just build a hydrogen detector? I'll touch on that, and you can ask me again later. It's a reasonable question. People are doing it, so maybe I should tell you why do this as opposed to why not do that. Okay, well, let's first talk about whether this is possible. So can you dissolve hydrogen in liquid xenon? Hasn't been done, but lots of stuff has been done. So this is a plot of, this is a complicated plot, but this is Henry's coefficient. So the amount of gas that is dissolved in the liquid for a given partial pressure of that gas above the liquid. In this case, we've chosen 1 atmosphere above the liquid. What is the mole fraction in the liquid? And there's a bunch of data. You will note there is no hydrogen and xenon on this plot. However, there are several things that are instructive. So in particular, I'll point you to the hydrogen and argon here in these triangles. There is helium and argon in those triangles. There is helium and xenon up here, well above the helium and argon. And so by sort of analogy, we're saying that at least the hydrogen and argon will likely also be up there. Turns out xenon is a pretty good solvent because it's nice and big. You can make lots of space in between it. So by the properties of noble gases, it's actually a pretty good solvent. And actually, it's the thing that we worry about, but it does preferentially bring impurities into it. One reason why xenon detectors are harder to purify than you might think they would be. Okay, so we think we can get something like 1 to 10% by mole in the liquid for this much gas and oil. So remember, what don't you need for this searches is a lot of mass. You only need about a kilogram. And so at this concentration, that's getting like at 10 tons. 10% by mole, you divide by another factor of 100 to get by mass. So that's 1/10 of a percent by mass. So 1/10 of a percent of 10 tons is a kilogram. You can't do that. So you can do this just by doing like that. Okay, so this gets to your question a little bit of backgrounds. So one problem with, say, a pure liquid hydrogen or liquid helium detector is that it will not shield itself nearly as well as the xenon does. So I'm trying to show you that in a bit of a complicated way. This is the interaction length for gamma energies of this energy, gamma rays of this energy in liquid xenon, where they interact very, very strongly, and liquid hydrogen, where they don't interact as strongly. And then you can ask, sort of by the same argument, how big is that interaction length compared to the size of your detector if you have 2 kilograms of hydrogen versus LZ? And so the answer is that LZ is very big compared to the interaction length of gamma rays because it self-seals very well. Whereas 2 kilogram liquid hydrogen is basically transparent, and there is no shielding of any kind. So gamma rays from anywhere will just go all the way through your detector all the time, and so your backgrounds are going to be a problem. So self-shielding is not effective in these pure small detectors. You have to do other things to get rid of the shielding. It's not impossible, but it's a downside. However, backgrounds, a problem with hydrogen is tritium. Tritium is chemically the same thing as hydrogen, but it's radioactive. It turns out atmospheric tritium is at about the part 10 to the 18 level. If you wanted to dope LZ with it, you'd have to get it down to a part 10 to the 24 level. So underground sources of hydrogen have been used in the past. This is sort of analogous to what people do in argon, for example. Or you can distill. This is actually sort of interesting, right? Hydrogen and tritium, because it's only got an atomic number of 1, there's actually a factor of 3 in mass between the 3, and so it's easier to separate them than you might think, considering that they're isotopes of each other. And so NuCap was able to suppress deuterium and hydrogen by several orders of magnitude, and so tritium would presumably be more efficiently removed. I think we can solve this if we decide that the rest of it's doable. Okay. So comment on signal detection. This is getting to the other part of the answer to your question about why do this here as opposed to somewhere else. So this is the sort of standard picture. I'm going to go over it because you can leave if you want. All right, so this is signal detection. How does this S1 and S2 production actually work in these detectors? So you have a recoil in your experiment, say for an electron recoil, that produces excitation and ionization. So the excited xenon atoms, it turns out that they want to live in molecular states, which then decay, giving you a photon. That's your S1. If you ionize, you get an ion plus an electron, which you can collect to S2. Or the ion and electron can recombine, which then actually goes down this path to give you another S1. So these are how you get S1 or S2. This will look exactly the same for a proton recoil. So hydrogen recoiling for the liquid will do exactly the same thing. You'll be able to detect the same S1 and S2 light. So that means you can keep the same detection scheme. So the same light you collected before with these 500 photons that you just bought for many millions of dollars, you can keep using. So that's really nice. All right, now what about the signal size? So this is something to delve into dark matter experiments that you will learn a lot about, and this is again one of Juan's comments about 9 years ago. So xenon recoils in liquid xenon lose a lot of their energy to heat. That is this path, nuclear recoil going down to atomic motion. That atomic motion is not collected as electronic excitation, it's just lost to heat. And so in fact, this is known as the Linhart factor or quenching factor, depending on what you're talking about. But something like less than 20% of the deposited energy actually can be collected as signal through xenon recoil and xenon. And the reason is that because xenon can bang in other xenon atoms, and those just move around and don't give you any excitation. Now, hydrogen is the lightest nucleus, and so that means for exactly the same reason that light dark matter is not efficiently detected by xenon, hydrogen will not give its energy to xenon very efficiently either, and so it will have fewer strong nuclear collisions with xenon. So much less of the hydrogen recoil energy will go into xenon excitation, or direct xenon atoms will go more to electronic excitation. Can we model this? So here's an effort at modeling it. So this is something called the Noble Element Simulation Technique, or NEST. It's basically a data-driven package that models signal processes and production of xenon. So they have data from helium, alpha decays, right? Alpha is just a helium nucleus. They have data from alphas, which they put into their model. It's at high energy because it's MeV scales, but it is real helium nuclei in flux, or in liquid xenon. There's also SHRIM, well-known sort of code in Windows for some reason that you can use to figure out the stopping and ranges of ions and materials. And although this is probably not the exact application they meant this for, you can still sort of get an idea of what's going on. And so you can calculate the energy lost to nuclear stopping, that's again heat, and electronic stopping, which again is signal for our purposes. So this is what a 10 keV xenon recoil looks like in liquid xenon. Note the scale. It goes something like a few hundred angstroms maybe, whereas a 10 keV helium in this case goes on sort of half a micron scales. So that's just the inefficiency with which helium deposits energy into xenon, the xenon nuclear. It goes to electronic stopping much more. So you can sort of put these things together and calculate what do you think the signal yields will be. In this case I'm using helium because that's what the NEST data was from, as a function of nuclear recoil energy compared to xenon. So the blue line is the total quanta, so that's electrons plus photons, the total amount of signal that's produced per unit energy for NEST in xenon. This is the blue line. And then the dashed black is the same prediction from NEST for helium, and then green is the prediction from SHRIM. And it's sort of a miracle that the SHRIM and the NEST predictions agree with each other so well. But the bottom line is you get something like a factor of 3 more signal for the helium recoil than you do for the xenon recoil. And it's even more strong for hydrogen. There's no hydrogen in NEST, but you can do the same thing with SHRIM, and you get something like a factor of 5 times more signal from hydrogen relative to xenon for the same energy. Okay. So one comment on more sort of microphysics. So you have this path where you can go through ionization, you can go through excitation, which leads to S1 and S2. It turns out that electrons give you more S2 than S1 relative to nuclear recoils. That's what's giving you the ER at our discrimination. Remember this plot? It's because you're getting these two paths. So what's going to happen to the S2, S1 partitioning for hydrogen? The answer is I don't know. In the most optimistic case, this is data from simulating bolometers, which is a different complete technology, but you can see a separation between light and phonons in this case, between alphas and heavier nuclei. I don't think we know what will happen for hydrogen. So anyway, just make that comment. Okay, so let's make projections because we all have projections. My projections are really good. So I used the SHRIM model, hacked into NEST. I used the full LZ simulation package and the LZ backgrounds. And I use LZ statistical tools to do this. For now, I assume electron recoil-like partitioning. So that is bad for background rejection, but it's slightly good for signal. All right. So first, let's look at energy thresholds. A comment, I'll talk about S2 only in a second. Now let's talk about S1, S2, which is with the classic analysis mode in Lux, or LZ and Xenon. How you collect both S1 and S2. So this is the energy threshold predicted in LZ for xenon, and the energy threshold for hydrogen in yellow, factor of 5 lower, so you can go 5 times lower the threshold in addition to the kinetic benefits. S2 only analysis is a way to lower your energy threshold. The reason for that is the photon detection efficiency, or S1, is only about 10%, whereas our electron detection efficiency is around 100%. So if there's an electron that's produced, you can collect it. We have a very high gain on the S2 channel. So that means you can get to much lower threshold if you throw away S1 and only look at S2 because you're much more efficient for collecting the signal down there. The cost is that you give up ER and our discrimination, but I've already given up ER and our discrimination in the hydrogen case by sort of hypothesis already. You are subject to additional backgrounds, but still very powerful. This is an example from DarkSide where they did this technique to get to very low mass sensitivity in a liquid organic detector. All right, so if you go to S2 only sensitivity, now your threshold is actually a factor of 8 lower than it was in xenon. So you can get down to something like 180 thresholds, hypothetically, with the hydrogen recoils. Okay, so let's turn that into a limit. So this is something like 250 lab days of 2 kilograms of hydrogen. So normally that would be, in the ideal case, like 2.5% molar fraction in the liquid, or at a tenth of an atmosphere partial pressure. Again, this number is not measured, so take all of this with a salt shaker of salt, is always the point. Anytime anybody makes dashed lines on a plot. This is the hydrogen projection, now going down to 50 MeV in limits. So here would be an S1, S2 analysis, and then if you go down to S2 only analysis, depending on what your threshold would be, Nice thing about using hydrogen is it's a proton, so it's got an unpaired spin by default. And so this is what it will look like in spin dependence density. These curves are actually in the exact same place because there is no difference for protons for the unpaired proton. And that's a really, really strong case of AFTs. All right. So what am I worried about? Actually, any questions before I talk about what I worry about? I'm doing great on time. No questions. Okay. Okay, we'll get to the exciting part now. The part where I have no idea what's going on. Okay, what do I worry about? I worry about cryogenics. This will become very important in a slide or two. But the amount of non-condensable gas running around in this condensable xenon will potentially cause a problem with how you cool your detector. I knew this was going to be a problem, but I didn't know how much of a problem it was going to be until a week ago. Purification. The existing LZ purification scheme will actually remove hydrogen. I think we can get around that, but that's going to be a problem. Suppression of S2 production. So with the H2 in the gas phase, that will suppress the amplification or the acceleration of electrons through the gas phase, and you'll get less S2. I think you could probably get around that by increasing the voltage, because for exactly the same reason that it's suppressing S2, it'll probably also suppress sparking, and so you get a higher voltage on your grids, but that will have to be tested. And hydrogen is flammable. If you're using it in a mine in large quantities, people might have problems with that, but I think that's an engineering job that we can probably fix. So, what's next? This is still fairly speculative. For example, the Henry's coefficients are not measured. Is there temperature dependence? What about diffusion? Will it mix well to liquid? And then, of course, all these signal yields depend completely on modeling and MEV scale data. There's no direct data that show purposes. So we need to calibrate and do some measurements. Okay, so this is a chamber we have at FNAL that was actually designed by Dan Baxter, based largely on another design in Michigan, but a little bit of Dan credit for this one. The idea was originally to test limits of electron recoil discrimination for inner shell latencies, which is the topic of a whole other talk, and I recommend you go ask him what that means. But it's got a single 3-inch BMT facing 4 1-inch BMTs, got some grids and some level meters, and it's got actually pretty good performance in the last year. So this is the single electron peak in my detector. We can resolve 2 millimeter pitch grids, although it doesn't exactly look good, that's not too bad. We have good energy reconstruction with good signal yield in this detector. There's a recent talk from a Northwestern grad student, Dylan Temples, and Taub on this detector and the measurement that was originally designed for it. But it's now available for doping. All right. So doping. We did this last Tuesday. So this is all new data. Everything I say here, I will willingly wash my hands of it in 2 more weeks when I understand things better. So we'll take everything as new and fun, and we'll see how it goes. All right. So this was the plan. The plan was we were going to inject some hydrogen, we were going to see it dissolve, and use the pressure change to tell how much it dissolved in the liquid. Again, we're sort of repurposing a system that's not set up to do this. This is what we thought would happen. So I made this lovely MATLAB program to calculate how much it would dissolve, blah, blah, blah. If we injected a PSI, I expected that we would see something like a total of a tenth of a PSI rate, rise in pressure, and all that would be attributed to the hydrogen dissolving liquid. Perfect. Okay. So this was the plan. This is what happened. So here's the hydrogen injection, that little guy. And then, nothing happened for a few minutes. We're like, oh, we're going to have to do this a lot more. I don't get to see anything. And then 10 minutes later, all of a sudden the pressure started going up and we lost cooling in the detector. So what's going on there?
It sounds familiar.
Yeah. So what's going on? So what's going on is we started concentrating hydrogen in the condenser. So this talk is now turned into a seminar. I apologize for people expecting a colloquium. We're going to talk about some technical issues. And again, feel free to leave if you want. Okay, this is what our geometry looks like. There's a detector, there's a condenser. This is where the cooling is applied. So gas comes in, hits the condenser, liquefies, drips down into the detector, and then sort of a loop. And if you want to purify, we can go out this way. Or if you want to take data, we open this equalization line so that the pressures in here are equal, and that sets the level in here to be where we want it to be. Okay, so what was happening when we put in this little amount of hydrogen? This is like something like 200 cc's of hydrogen at STP. So it's not like, it's something like 20 milligrams of hydrogen. So, okay, it starts mixing in the detector, runs around with the xenon, hits the condenser, the xenon drops out, the hydrogen stays because it's not going to condense, and all of a sudden it starts blocking the condenser from the hydrogen, or from the xenon can no longer be cooled, because we can no longer cool the detector, all of a sudden the heat loads of the detector start rolling it off and the pressure starts to rise. Okay, so that's what happened. Fortunately, we can circulate. And so what we did is we turned on circulation, and that seems to mix the xenon and the hydrogen enough that some xenon can actually see the condenser, and we did not blow up all our burst disks. So that's a relief. We didn't destroy the detector immediately on doing this. Okay, so then we thought about it for a while. I went to the library and I was like, oh, there's 1,000 papers on condensing things in the presence of non-condensing gases. I knew this was going to be an issue in my defense, but I didn't think it would happen at this level. Okay. So now we think we understand a little bit better. So this week we did it again. So we took the xenon, the hydrogen out with a getter, that we usually use. Now we tried to do it in a little bit more controlled fashion this time. So Tuesday and Wednesday, I guess Monday and Tuesday, because today's Wednesday, right? We did some more injections and waited a few hours. And it turns out that we were using circulation to mix the hydrogen and the xenon continuously while we were doing this. And it looks like the cooling power of the detector is sort of linear with the mass of hydrogen injected, or the pressure. So this is the detector pressure versus the total hydrogen injected. And so if people want to think about what's happening, well, let's talk about it again if people are actually interested in this. I think we have models for this already, but okay. So we've got 100 milligrams in the detector so far. That's something like 0.2% of the mole fraction, and my projections were based on something like 1% mole fraction. So we're in the same order of magnitude, but we're not quite close. And unfortunately, our burst disk, the pressure relief on this thing is up at 35. We don't want to get that close because xenon is crazy expensive. We don't want to lose any of it. So we want to keep the pressure below 30. So we're not going to be able to get all the way up to what we wanted to do. So this is a start. All right. All right, what's going on? First of all, the TPC still works. So that's a success. These are some electron lifetime plots. So the electron lifetime you can measure by taking S2 as a function of drift. And so the electrons that start at the bottom of the detector have to go through the full detector. Some of them are eaten by impurities on the way. So that's called the electron lifetime. And then the S2 side at the top. So this is all the same energy was deposited here, but at the top of the detector you see more electrons than at the bottom because some of them get lost on the way. Okay. So this is the electron lifetime at the very beginning of Monday. This is the electron lifetime yesterday, also in the morning, but after we've done, I guess, 6 injections. And they're very similar. There's maybe a small loss in purity. We'll come back to that. We do see some S2 yield drop. So here the mean S2 at the top is something like 12,000. Here it's like 8,000. So again, that was expected. So that's good. We do see some loss of purity. We attribute that to contamination in the hydrogen bottle. The reason for that is because we did purify it back out with the getter, and we didn't see the lifetime recover immediately. So that's water got in and didn't come back out. There's a possible decrease in S1 yield. Luca asked me this question when we were talking. I was like, yeah, I should definitely answer that. So about 10%. That could be really troubling if it persists or if it keeps going up with the amount of gas we inject. I was not expecting that, so that's the thing to watch. Right. But I think bottom line for now, TPC is still working. All right. Is hydrogen in the liquid? Big question, right? Remember the original plan was we were going to be able to easily see the hydrogen dissolve because the pressure was going to drop. But of course, as soon as we put hydrogen in, the pressure went haywire, so we can no longer use that method. And I've been spending the last week counting our Slack channel, thinking how the heck can we prove that there's hydrogen in the liquid? And there's no easy way because all the time scales are wrong. So the one thing I do have is we're able to put an RGA on the gas phase. Okay? So an RGA is a gas analyzer. So this is a scan of the gas phase just after injection, but before inducing mixing. So by inducing mixing, what I mean is forcing the circulation through. You can force the circulation either just through the gas phase or you can force it through the liquid. So when we force it through the liquid, that's for maximally mixing the liquid and the gas. Okay. So before we induce mixing, there's the hydrogen level here is 10 to the minus 5 in some units. This is not a calibrated scan. We don't have a calibrated sample. This is not the right RGA for hydrogen usage because there's a whole bunch of calibrated scenarios. So 10 to the minus 5. When we induce mixing, that goes down to 3 times to the minus 6. So there's a factor of decrease in the hydrogen we see in the gas phase when we induce mixing. There is hydrogen in the liquid, at least during this period when we're mixing. Okay, so the answer is yes, although it's hard to say exactly how much. And until I can say how much, it's going to be hard to really say. But I guess the first order, our first experience is the TPC didn't break. Hydrogen does go in the liquid. I'll stop there. Okay, so what next? Thinking about it. Do we need to change the condenser geometry to explore larger concentrations? So an obvious thing to do would be to cool the liquid directly. Then you don't have to rely on the stupid condenser. Or you could change the geometry to be more efficient with the condensable gas in there. There's a couple of things I think we can do, but they will require surgery. How do we measure the liquid concentration directly? An easy thing to do there is probably to put an RGA line directly in the liquid. Again, that requires surgery. Is there another clever way to do that? I'm not yet thinking about it. Can we observe hydrogen recoils in Zelda directly? So this is an idea. Maybe we can put up a neutron source. The hydrogen recoils off the neutron source will be super high energy and also super high in yield, so they may stand out really clearly if you can separate them from all the backgrounds and make them think of that. Problem is that I'm moving to California on Monday, so we'll see. Anyway, so that's been fun. That's basically the conclusion. So a few conclusion slides, then we'll go on. Okay, so hydrogen dumping in xenon. It is physically possible, I think we've shown. I think you can keep the low background level achieved like the xenon TPCs. That's a big thing. We've just spent $50 million, but it is incredibly low background environment. We should use it for more than just what we originally thought. We can get the same signal readout with the liquid xenon sensor light detectors. I claim to get increasingly low from hydrogen recoils. I used to get this talk about helium. Lower energy thresholds for when hydrogen scattering. And you can get below 1 GeV dark matter. However, there's obviously a lot of work that needs to be done. On LZ, construction's in full swing. TPC is complete. Detector is moving underground in October. Of course, xenon antenna and Pan-X are also under construction, so I think the next year will be interesting for the field of dark matter. Everybody says that at every talk about every year. You know, this one is actually true, I think. And then light dark matter, the slides I skipped over, is a hot topic. I think hydrogen doping is a promising idea of many, but there's lots of improvement. So this is the LZ collaboration in South Dakota. That's quite a West place. It is not in Frontier. This is the Zelda team. There is Dan, who's not Chicago. Thank you.
I have a first question actually related to this. So in PICO and the laboratories, we're actually thinking of using hydrogenated refrigerants to do something similar. And we plan to do that after the standard run with another refrigerant that does not take hydrogen. So my question for you is the collaboration behind the, I mean, because the smaller these politics, maybe somebody else wants to do something else with it.
Somebody else does want to do something else.
So what's up? Tell us that backstory then.
So somebody else wants to freeze it,
Freeze it?
which I think is nonsense.
Okay.
Well, it's not nonsense. It's good.
My vote is for putting hydrogen.
Yeah, so I want to burn it. And he wants to freeze it.
Freeze it.
Yeah, so if the idea behind freezing it is that the biggest background in LZ is going to be radon. And so the claim is if you freeze it, you can then freeze the radon in place and tag the daughters. Sort of like what Dominic does at some level, right? However, if I think the cryogenics for hydrogen are a problem, the cryogenics for freezing LZ are also a big problem. So we'll have to fight that out later. I can say that the collaboration is certainly interested in this. And so other people are trying, we put in a proposal, you know, to the DOE basic research needs, which some of us in the room are heavily involved with. Just like everybody else in the dark matter community put in a proposal to that. And on that proposal, I had all the national labs signed on, including the spokesperson of LZ. So I think, I actually do something, you know, maybe I'm naive. I think if we showed that this actually could work, which we're obviously a long way from doing, I think there's actually a good chance we can convince LZ to do it. Because, you know, we've done a lot of work building this detector, we want to use it as much as possible.
Could you go back a slide, please, or maybe 2 slides? Sort of your conclusion. Yeah.
This one?
Right there. There. So, light dark matter is a hot topic. And I guess this, so you have some detector. You know, the saying, when you have a hammer in your hand, everything looks like a nail. If you were starting over, if you didn't have these detectors, is this the way you would pursue it?
Is, if I were starting over and I wanted to look for light dark?
Light dark matter. I mean, is this, I don't want to say is this worth the effort, but is this worth the effort? or are there, you know, I appreciate what you've done in the technical way.
Are you asking, is light dark matter worth the effort?
No. If you think light dark matter is the way to go,
Yes.
is this approach the approach you would take if you wouldn't already have this?
No. If you didn't already have LZ, you would not do this, because why would you just be so crazy as to build LZ to do this, right? No, I completely agree with that. You do something else. However, because LZ is going to exist, and all of the light dark matter experiments are having these background issues that are new, right? They're pushing technologies in places that we don't have any understanding of. There's noise, there's weird, there's all this stuff that's coming up in the background world that is new. That I think something like this would not have, because it's, you'll run LZ, you'll have fully characterized the radioactive backgrounds as well as anything, any radioactive background environment has ever been characterized. Then you add your hydrogen. And you're piggybacking on all of this infrastructure that already exists that will help you understand your backgrounds before you go into it. And so I think because that will already exist, that's why this is valuable. I wouldn't start out with this, but given LZ, I would use it.
Okay, fair enough. So a related question. So you're going into unexplored territory at lower mass. So I don't think you should just only go into unexplored territory that's theoretically motivated or something like that, but that might be the first place to look. Do you have theoretical predictions for the area you're going to be in?
Do you mean, is there a theory that we're sort of
probing?
probing?
Right. Are you shooting for anything?
I am not shooting for anything in particular. I mean, the usual class of models that lives down here, so things like asymmetric dark matter or these the freeze-out models,
The freeze-in models?
I don't know if I get all the way down to freeze-in models, actually. So I would say, I'm not looking for a specific model. I take counsel from my theoretical colleagues that say there are interesting things in this region, and so therefore...
If you find something, we can find a theory for it.
Yeah, that's the way I look at it. So I'm not looking for anything in particular.
Okay, fair enough.
Yes.
So for Zelda, you were saying the pressure, like there was a big pressure spike, so you could get as much hydrogen as you wanted. Is there then something else you're considering injecting instead, perhaps? That's like, a little bit more intermediate, where you can get that last bit?
So that's an interesting question. I would say the reason we can't get as much in as we wanted is because of the particular cryogenic geometry. So it's not a fundamental limitation of the hydrogen and xenon combination. Now you could ask, given that Zelda exists and we don't want to mess with it, could we try something else? And I think the answer is that almost anything that you put in that's not condensable will have this problem. Because if you did helium, it would immediately have this problem as well. You could imagine something that dissolves more readily, and so there's less of it in the gas. But by then you're getting farther away from where you want to be anyway. So I think it's not worth. The only thing I would say it might be worth doing is to use methane, because then we can use tritiated methane as a tracer to know how much is in the room. That's a different answer than you're getting at, right? So that would be a way to directly answer how much dissolved, but not because of the pressure or the condensation.
Is the background that you use in your estimate the same as NACS, or are you including the fact of loading so that you will be more fast?
So for now, I am not including the effective doping. So I'm assuming I can get rid of treatment that comes with the hydrogen. I'm assuming that other than that, the hydrogen brings no other background. So there's S2 producing backgrounds. We don't know what they look like yet. So the S2 only, I think, are very speculative. S1, S2 actually, if the yields are there, I feel pretty confident about. Because outside of tritium and the hydrogen, I don't see what else background-wise the hydrogen brings with it.
What about me? Like, are you propagating the neutron flux? Like,
No, you're not. I
so
did not.
you don't know about nuclear recoils induced by neutron on you're not accounting that.
I'm treating nuclear recoils. No, but the neutron rate is good. So the neutron rate in LZ is very low a priori. So I'm using the known rate of nuclear recoils as a background, but not the rate of nuclear recoils on activity, which will be a factor of also low because the mass is low.
And nothing else will be pop up. You don't expect it.
I mean, I will not say guarantee, but I don't expect them to. Not to say that if a graduate student wanted to spend 6 months checking all this, yeah. Yeah.
In terms of detecting like dark matter, what are your thoughts on axion dark matter?
What are my thoughts on axion dark matter? I think they're good. I think axions. If I were starting out now, as opposed to 10 years ago, I I might join Axiom. I might still join Axiom. I think they're very interesting. I will say that one of the things that I love about Axioms is that there was, or at least there has been, a well-defined target, and that target seems to be getting easier as the theorists get at it. I don't understand how to interpret that, but basically, if there was like a really nice target, I'd be like, yeah, let's do it. But in the last 5 years, all of a sudden, all those bounds are gone too. It's not like, well, you know, it's just another dark matter candidate. So I think axiomatic stars are really interesting. That's the, yeah.
There's no more questions. Let's thank our speaker again.